And lastly, our last set of equations here, these are all logarithmic, but unlike the previous logarithmic equation, we won't be able to write log equals log. So in that case, we need to use the definitional logarithm going the other direction. So we'll have something of the form y equals log base b of x, and that's going to imply that x equals b to the y. So in your non-one-to-one properties, if you have a log, you change it to an exponent. If you have an exponent, you change it to a log. In the one-to-one properties, the other two videos, if you have the same base, you set the exponents to be the same. If you have the same log, you set the arguments to be the same. So there are some parallels going on here between all four types of problems: exponential logs, one-to-one, not one-to-one. So in part A here, we have a logarithmic equation because the variable's inside a log, but we don't have log equals log. So in that case, we're going to need to use our our definitional logarithm here. To do so, remember the base of the log is the base of the exponent. What's the base of the log if it's a natural log? E. So the base of the log is the base of the exponent, so the base of the log is E. The base of the exponent is E, so we'll say E to the 6th equals 2x plus 4. So our little swirly thing, E to the 6th is 2x plus 4. E to the 6th is a number. It's not a pretty number, but it's a number, so leave it alone. This is a linear equation because the exponent is a 1. So to solve for x, working outside in, what are we going to do to the 4? We're going to subtract it, and the 2, we'll divide it. So your final answer is e to the 6th minus 4 all over 2. Remember, e is about 2.7 something. I don't know what e to the 6th is, 30, 40, I don't know exactly. But we have to check. If our e to the 6th, let's just say 30, even though it's a very big underestimate there. If it's 30, 2 times 30 is positive, plus 4 is even more positive. So if I put it back in, I'm totally fine. In part B, to use this property, what's the coefficient of the log have to be? 1. What do you have to do to the log? Like, can you add or subtract to it? Nope. So in order to use this rule, the definition of log, you must isolate the log first. So working outside in, what are we going to do to the negative 7? And then what are we going to do with that 2? We're going to add that 7 to both sides, and then we're going to divide by 2. So if we add 7, we get 13. Dividing by 2, we get 13 halves. So now it's prepped for funness like in part A. The base of the log is 3, so the base of the exponent is 3. So 3 to the 13 halves equals x. And then this is done. You can stop this one right now. If this were a nice number, like if that were 3 to the 3rd equals x, then I would ask you to write that as 27. But 3 to the 13 halves is not a pretty number, so you can just leave it alone. You don't have to rewrite it anyway. In part C, notice on the left-hand side we are adding logs. If you are adding logs, what do you do to their arguments? You multiply them according to the product rule. So the left-hand side becomes log base 2 of x squared minus 2x, because we distributed that x through. Okay? So, since we have log equals number and not log equals log, just like in parts A and B, we have to write it as an exponent. The base of the log is 2, so the base of the exponent is 2. 2 to the 3rd equals x squared minus 2x. 2 to the 3rd is x squared minus 2x. 2 to the 3rd is 8. If I brought that 8 over by subtraction, and then factored, setting each factor to 0, I get 4, and and negative 2. Is 4 okay? If I put 4 back into the original arguments, do they become positive? Yep. This gives me 4, this gives me 2. If I put in negative 2 into either of them, I get negative arguments. So negative 2 is not a solution. So in all 4 cases, we could not have log equals log. We ended up with log equals number. So in that case, we need to use definitional logarithm to write it as an exponent.